Hey everyone, in this AP Chem series video, we're going to take a look at a special type of intermolecular force called a dipole-dipole force. So remember from the last video that there's a lot of different types of intermolecular forces. Here's our complete list from the last video. In this video, we're going to focus on just one of those known as the dipole-dipole force. A dipole-dipole force is the name given to the attractive force that's going to exist between two or more separate polar molecules like the hydrogen fluoride molecule shown. So if we had multiple hydrogen fluoride molecules that could be attracted to each other, according to Coulomb's law, the negative pole of one of those molecules would be attracted to the positive pole of another, and we'd call that attraction a dipole-dipole force. Here's what that might look like if we did have two separate hydrogen fluoride molecules. Notice the partially negative fluorine atom is what's being attracted to the partially positive hydrogen in the second molecule. The attraction is typically represented with a dashed or dotted line, and that attraction would be called a dipole-dipole interaction since both molecules are polar. And there doesn't have to be just one dipole-dipole force. If we had a third hydrogen fluoride molecule, it might also be attracted to the one in the middle, and that would also be a dipole-dipole interaction since both molecules are polar. This description of dipole-dipole forces is definitely one of the key ideas for this video. Make sure you take some time and write it down. Now, a lot of the time what we have to do is not just look at one single dipole-dipole force, but look at different types and compare them in terms of which one is stronger. To do that, the strength is based on two things, the magnitudes and the orientations of the dipoles. Let's start off and look at the orientations of the dipoles and what that will tell us. So here's a model showing four separate hydrogen chloride molecules. Chlorine is the more electronegative atom, so it's going to pull the shared electrons closer to itself, creating a partial negative on the chlorine and a partial positive on the hydrogen. So if you look at these two molecules on the right, you'll notice that the partially negative chlorine is oriented almost directly towards the partially positive hydrogen in the second molecule. That's an orientation that's going to lead to stronger attractions since the negative and positive poles are directed towards one another. On the middle two molecules, however, the partially positive hydrogen is not directed towards the partially negative chlorine, so those two molecules might experience some attraction, but it's likely to be much weaker than the other. Now let's take a look at what we mean by the magnitudes of the dipoles, and we'll do that by comparing the dipole-dipole force that would form between hydrogen fluoride molecules and hydrogen chloride molecules. So to do this, we have to start by comparing the electronegativities of the atoms to see just how polar these molecules are. We could go to a periodic table and look up the actual electronegativity values, but here we don't really need to because the HF molecule has the atom fluorine, and fluorine has the highest electronegativity out of any atom on the periodic table. That means the difference in electronegativity between hydrogen and fluorine is going to be much larger than the difference in electronegativity between hydrogen and chlorine. And that means that the fluorine atom is going to pull on the shared electrons in this bond much more strongly than the chlorine atom will. So that fluorine is going to develop a partially negative charge with a greater magnitude than the chlorines will. Or another way to say it is that the hydrogen fluoride molecule is more polar and the hydrogen chloride molecule is less polar. And finally, since the partial negatives and partial positives in HF have greater magnitudes, that's going to be the stronger dipole-dipole force, and this will be the weaker of the two. We can summarize all of that by saying that a larger difference in electronegativity leads to a molecule with a greater dipole moment, and that greater dipole moment leads to stronger dipole-dipole forces, another one of our key ideas for this video. And that actually wraps it up for dipole-dipole forces. Thanks for watching, and here's a brief summary.